So good afternoon or good evening, everyone. My name is Iuliana Laura Calugaru. I'm a project manager in CETRI and a college chemistry professor. And the title of my presentation is Half-charring of dolomite mineral for applications in the passive treatment of mining effluents. CETRI is a college center for technology transfer who offer technical supports in development and or optimization of processes in mining and industrial sector. We are located in Quebec, Canada, and surrounded mainly by mines, metal mines and forests. Our mission is to explore, identify, and propose innovative solutions to valorize underused natural resources, byproducts, industrial waste in a sustainable way through responsible business practices. So the outline of my presentation includes the context, dolomite characterization and its half-charring, and then half-charred dolomite characterization and applications, and then a few conclusions. So the context is the environmental impact of the mining activity, and among the most important impacts we count the waste rock, the tailings from mineral processing, the mine drainage, and the sludge from water treatment plants. We know that the contact between waters and the components of the mine like pit walls, waste rock piles, tailings, access roads, and generate effluents contaminated through mineral dissolution, what we call mine drainage, and we classified it according to the pH in acid mine drainage with a pH below to 6, contaminated natural drainage pH between 6 and 9, and basic mine drainage pH above 9. This drainage has a season-impacted and variable flow, and its qualities depending on the mineralogy of the site, climate, mining operation, for instance, underground mining or open pit. The charge is variable concerning metals, metalloids, sulfate, and the environmental impacts may persist hundreds to thousands of years after the mine closure. Because the mine drainage may contain significant concentrations of metals, metalloids, and anions, which are potentially harmful for humans and environment, the treatment is mandatory. And if we have mines in operation, this is done in water treatment plants, but after the mine closure, there is the sustainable option and low-cost option is the passive treatment. We call it also pseudo-natural because we do the contact between effluent and materials by gravity flow. We use local materials widely available in order to reduce the transport cost and the the environmental footprint of the transport. We use byproducts, residue, natural materials, underused materials, and the target is to have low operation and maintenance cost. And also an issue is the stability of saturated materials. So there is an ongoing research for treatment technology to reduce the environmental footprint of mine water treatment. Among the passive technology for acid mine drainage and contaminated natural drainage treatment currently available, we count open limestone channels, wetlands, biochemical reactors, limestone drains, and even a combination of the above technique, what we call multi-step treatment, when the quality of the mine drainage requires a multi-step treatment, because sometimes the mine drainage is so contaminated that only one treatment is not enough. Multi-step with a few techniques is required. Among the materials, actually the most employed and the material that we use in I think maybe all the systems that I counted here, we have carbonates. Carbonates are important to neutralize and increase the pH of the water, to reduce the acidity and increase the alkalinity, and to remove contaminants by precipitation, co-precipitation, sorption, ion exchange. And here we have two chemical reactions. One is for the case case of using the limestone, which is the most employed in acid mine drainage and contaminated nodal drainage treatment. And the second one, dolomite, which is the subject of my research. The dolomite is interesting because it's less subject to the hard pan effect of gypsum. So the first reaction, the reaction of the limestone with sulfuric acid, which is generated in the process of sulfide oxidation, which is responsible for acid mine drainage generation. So we have ion in solution like calcium and sulfate. They will precipitate in the form of gypsum that will passivate the stone, the dolomitic stone, and this will stop the neutralizing the chemical reaction. For the case of dolomite, the risk is lower because magnesium sulfate actually is soluble. So here I have two qualities of dolomites. One is that the dolomite I used in my PhD, and the second, the dolomite that I'm currently using in my research project that I'm doing now in CEDRI. Why I decided to present you both qualities of dolomite, because I wanted to show that even if the dolomite has a different, the dolomite rock has a different composition and purity, the result is the same. So the product, the half-charred dolomite, can be obtained. So the first one, the first dolomite rock contained 87% dolomite, and the rest was silicium oxide and silicate. The second one was more pure, 96% of dolomite and some calcium carbonate, and then little silicate and silicium oxide. And I have here the X-ray diffraction of the dolomite rocks. And I did half-charring of dolomite sample 1 during my PhD. I started with the thermogravimetry analysis because I wanted to have an idea at what temperature I could start my testing, but it was difficult to interpret because the purity of the dolomite was not, of the dolomite rock was not very high. So I knew that I want to stop after the first reaction, because the idea of half-charring is to decompose magnesium carbonate in order to obtain dolomite stones consisting of calcium carbonate and magnesium oxide. But we do not want to decompose to go to the second reaction. We do not know to decompose calcium carbonate, which is the backbone actually of dolomite stones. So the idea is to keep the mechanical strength of the dolomitic stones and to transform dolomite in a more reacting material consisting in calcium carbonate and magnesium oxide. So theoretically, if we look at the stoichiometry of the decomposition of dolomite, the mass loss by 1 mole of carbon oxide is 23%. And for the first sample, which contained 87% dolomite, the mass loss is 20%. So the experiment is only heating the dolomite in an oven and follow up the mass loss. So I did what is done in the literature. I look for 3 temperature and different times of heating. We do not go above 800 Celsius because we risk to decompose calcium carbonate. So this is my 3 temperature. And for the second one, because I had some knowledge acquired during the experimentation with the first sample, and because the thermogravimetry was easier to interpret, I was able to figure out that at the temperature of 780, I could decompose magnesium carbonate. So I only investigated 3 temperature for 1 hour because we noticed that actually we calculated that is more expensive to heat longer than to heat at a higher temperature. And because my X-ray diffraction and my thermogravimetry were done on powder, we were thinking that if we have dolomite stone, it's better to use a little bit higher temperature in order to decompose, to maximize the decomposition of magnesium carbonate. And here we have the results. The X-ray diffraction showed us for the first samples that for the dolomite charred heated 1 hour at 750, we succeeded to decompose a lot of dolomite minerals, so the remaining is only 7%. And then we have 53% calcium carbonate and almost 20% magnesium oxide. Also, the specific surface, which is a very important parameter in chemical reaction and absorption and neutralization, we obtain a 7-fold increase. The values here are not the real value for the dolomitic stones, because we had to put it into powder in order to analyze, to do specific surface analysis. But what is important is the 7-fold increase of the surface. And for the second, the result was even better. We had 63% of calcium carbonate and 26% of magnesium oxide. The first parameter that is easy to investigate is what we call paste pH, which is the pH of the water into contact with dolomitic powder in a ratio of 50-50%. And we noticed that we succeeded actually to have a higher paste pH because of the magnesium oxide actually, and we have dolomitic stones that can be used in the system, the treatment system with a flow. For half-charred dolomite powder, there are applications described in the literature, many articles and that highlight the dolomite, half-charred dolomite powder efficiency for water treatment, gas absorption, soil remediation. However, for half-charred dolomite stones, there are not much literature. And what we can conclude is that we are able to prepare dolomitic stones, half-charred dolomitic stones, by heating dolomite in 1 hour at 780 for the second sample and 750 for the first one. And the new material is more reactive and better neutralizer than the raw dolomite, since we have actually magnesium oxide, which is more reactive than carbonate. We have magnesium oxide distributed on the backbone of the calcium carbonate. And this new material actually is currently is evaluated for acid mine drainage and contaminated neutral drainage in treatment systems like the systems that I mentioned before for mine drainage treatment in field condition passive treatment. So here we have some references, my paper, my research work on the subject. And now thank you for your attention. And also we would like also to thank to our partners.